Good afternoon, good evening, good morning, depending on where you are in the world. My name is John Josephakis. I'm the Vice President of High Performance Computing Sales at NVIDIA. Excited to have you join us for this SC21 special address. It's been another exciting year with many announcements following our GTC event and now with SC21. It promises to be a very exciting time for all of us in the high performance computing community. It is the first event actually after a long time where NVIDIA is participating both in a virtual way, but we also have a small presence at SC21 to meet our customers, our partners, and of course our HPC friends. Over the last year, we have had many announcements around our technology on the hardware platforms with our Grace ARM CPU, with our A100 and different options there, and also with our NDR networking devices. But in addition to that, we have announced a lot of many software initiatives and different areas of research. In addition to that, we continuously invest in research computing, in HPC, and how data sciences is becoming part of our modeling and simulation. In all areas, we see that data sciences are making a big difference in ability of people to solve larger problems with larger systems. In areas such as edge computing, quantum computing, weather and climate, and alternative energy, just to name a few areas of focus and work. Today, we'll have the opportunity to hear from a number of NVIDIAns about some of the advancements that we're making. And in addition, we'll have the opportunity to talk about specific technical sessions that will be addressed at SC21. And 1 week ago at GTC, we had a lot of events that please feel free to go and watch and see. But even more, we'll have more sessions around Supercomputing 21 that you are able to watch. Catch us also on the floor or at our meetings, and we'll be glad to discuss with you either face-to-face or a one-on-one call as we go through this next few days and weeks. But with that, I'll pass it on to Mark Hamilton, and he will take it from here and go into our presentations. Thank you so much, and again, look forward to a very exciting SC21. Thank you.
Thank you, John, for that great intro. And let's go ahead and head straight into the talk. I'm Mark Hamilton, and today I'm going to talk 4 quick chapters before we open it up for Q&A. If you have questions, please go ahead and place your questions in the Q&A box. Our moderators will be listening to them, and we'll get to them after these 4 sessions. I'll jump right in and talk about full stack accelerated computing, a technology NVIDIA pioneered over 15 years ago. We'll then move quickly to talk about cloud native supercomputing, million-x acceleration in science, and finally, cap it off talking about Omniverse and how Omniverse plays in the supercomputing space. There's a new computing law that's started. Moore's law has come to an end, and we need new innovation in high-performance computing. NVIDIA's been leading the way in accelerated computing for 15 years. And we've been here supercomputing after supercomputing, talking about advances every year. And what we've been driving remains the same. We continue to be the leading accelerated computing company and continue to drive increases in performance. But there's 2 new things that are happening. The data center is really becoming the new unit of compute. Supercomputing today isn't just about a chip or an accelerator. Supercomputing isn't about building the fastest node. Supercomputing is about scaling out at the data center level. And that requires, of course, the compute nodes, the storage, the networking to all work together and work together with millions and millions of lines of software code. So between accelerated computing amplified by scaling out and up across the data center, on top of that, we've now added machine learning. In the early days, machine learning was just about data science and data analytics. And there's many advances going on in that space. But today, we see machine learning applied not only to data science, but to traditional scientific computing. And we'll talk about some of the advances in that space. NVIDIA today truly is a full stack computing company. It's not just about one or two or three amazing chips. We're excited about all of our chip families, the GPU, our new ARM-based CPU, and of course, the DPU for networking. But that's just the start. We have over 150 SDKs. I'll get to talk about only a few of those today, but our SDKs today serve multiple industries: AI, cybersecurity, 5G, robotics, telecommunications. In all of these industries now are applying supercomputing and high-performance computing. Just in the last year, since SC20, we've introduced over 65 new or updated SDKs. We're now up to 3 million CUDA developers and over 30 million CUDA downloads in over 2,500 accelerated applications running on the NVIDIA platform. NVIDIA is all about our partners, and we're so proud to be here at SC21 with many of our partners and even many more joining virtually. I'll talk throughout the talk about how we're working together with partners to make our solutions even more powerful. But let's talk about real performance, not just on one application, but on a basket of over a dozen applications representing data science, high-performance computing, machine learning, and deep learning. The chart on the left is a geometric mean of the speedups. We've delivered 16x performance improvement in 6 years over 3 generations of GPUs, from the P100 to the V100 to our latest A100 Tensor Core GPUs. If you look closely, especially at the V100 and A100, you'll see that year over year on the same exact GPU, we continue to increase and improve the performance. What other platform today can you buy and on the same hardware have improved performance every year? Today, NVIDIA really is the world's leading HPC and AI platform. In the AI space, there's been a new benchmark that's emerged over the last several years, MLPerf. And NVIDIA's come in #1 in all of the MLPerf benchmarks, not only for training, where you would expect NVIDIA to be #1, but also in inference. And we'll talk about continued improvements and increases in performance in inference. And finally, this morning, as every year at SC, we celebrated the latest version of the top 500 list. NVIDIA today has more systems on the top 500 than ever. 71% of the top 500 systems use NVIDIA technology, and 23 out of the top 25 Green 500 systems. We see other new benchmarks coming out as well, and we're very proud to be participating in all of those. NVIDIA has announced more exascale AI supercomputers than any other company. Some of these, like Summit, still place very high on the top 500 list, and others were just installed this year or will be installed soon. Around the world, from Europe to the US and Asia, customers are choosing NVIDIA for their exascale AI computing. And finally, research breakthroughs. 4 of this year's Gordon Bell finalists, as well as the Nobel Prize in Physics, were won on top of NVIDIA technology. Here's an announcement we just made last week. One of the most commonly used commercial HPC applications, Ansys Fluent, now available on a new GPU-optimized version. It's an amazing value prop. Using the new GPU-optimized version running on a single DGX A100 with 8 A100 Tensor Core GPUs compares to 2 racks or 30 dual socket CPU nodes. That provides 10 times more energy efficiency and 5 times better cost of ownership. ANSYS is seeing great reception to the beta of this product, and we really look forward to seeing it adopted by ANSYS's thousands of customers around the world. One of the hottest topics in supercomputing are supercomputers of the future, quantum computers. But of course, much work is still left to be done before we actually develop a real quantum computer that's commercially viable at scale. Today, we're very proud to announce the release of the cuQuantum public beta, integrated with leading quantum frameworks and simulators from IBM and from Google, and more quantum frameworks coming soon. We've been working with all of the leading industry and research community partners. This is a space where we're partnering more than anywhere. Let's talk about how cuQuantum is accelerating quantum circuit simulations that'll be needed to build new quantum computers. We introduced the DGX Quantum Appliance. This runs on the DGX A100 and similar HGX A100 servers from our OEM partners. The speedups are truly transformational. Here we show some benchmarks reducing the time of compute from minutes to seconds. But real quantum simulations today that take months or more to run can now be run in days. This will enable much faster progress towards future quantum computers. Out of the box, our DGX Quantum Appliance is optimized for Google's CircuQ system, and many more simulations plan to be optimized for this in the coming months. NVIDIA researchers, though, haven't been standing still. We set a new world record, simulating 8 times a larger qubit system, 1,688 qubits, that was ever had an exact quantum simulation before, using cuQuantum running on our DGX Quantum Appliance. This was done using the popular simulation of the max-cut algorithm. We were able to simulate over 3,000 vertices. These are the types of breakthroughs in quantum simulation that will really move forward the development of future quantum computers. This system will be available starting in Q1 of next year. Switching gears a little bit, we'll talk later how our HPC SDK, of course, supports industry standard languages such as C and Fortran that so much HPC code is written in. But you know, there's many new programmers in the world. And if you went to university in the last 5 years, you're probably writing your scientific computing code not in Fortran or C, but in Python. And I get a lot of laughs sometimes when I talk to a Fortran programmer about writing fast Python code. It wasn't possible before. But let's talk about what NVIDIA's done with NumPy, one of the most popular packages in Python for writing scientific code. We've introduced the cuNumeric SDK. cuNumeric automatically accelerates Python code and is a drop-in replacement for NumPy. We've tested this running at over 2,000 GPUs. This will open up a whole new world of GPU acceleration for a new generation of scientific programmers writing in Python today. The automatic parallelism for this not only supports multi-GPU parallelism on a single server, but also supports multi-node acceleration across multiple GPU servers. And of course, it not only uses the GPU, but automatically runs the code across all the processing elements of the server, the CPU, the GPU, and even the DPU cores. Now, of course, back to Fortran in C. Wanted to give an update. 3 different ways, of course, to program the NVIDIA platform. 15 years ago, we started with NVIDIA CUDA, the parallel API that is still the most widely used in the world. For many years, NVIDIA supported OpenACC and OpenMP, directive-style languages or enhancements to languages. But today, for programmers starting out in standard languages, we believe the standard parallel extensions in Fortran and C, and there's more of these going into every new version of the standard, are one of the best ways to program accelerated computing. We don't believe there's any need for yet another parallel programming API when parallelism is now based in the languages themselves. Anyhow, all of these models will continue to be supported by NVIDIA moving forward. One of the most common data structures in scientific computing is the graph. And data scientists can now use graph neural networks to learn both the structure or to process both structured and unstructured data. And of course, graphs, when taking structured or unstructured data and representing that as a graph, is an inherently sparse representation. A perfect problem to run on our Tensor Core A100 GPU with sparsity. There's a number of things that we're accelerating. In here, we're using DGL, Deep Graph Library, coming from another one of our partners, Amazon. We've accelerated it with the CUDA-X framework and provided a number of different breakthroughs. Finally, let's talk about NeMo Megatron. NeMo Megatron is a great example of a new class of AI problems, and yet a new performance curve. If you look at all AI applications that have been popularized over the last 10 years, we see about a 25x a year increase, or doubling 25x in performance needs every 2 years. However, a new class of natural language processing and transformer-based applications are seeing a doubling, or every 2 years are seeing an increase of 275%. GPT-3 from OpenAI is a great example of that. And of course, the latest Megatron Turing natural language model released by Microsoft and NVIDIA together is the first public model that runs on representing over 500 billion parameters. On NVIDIA's Selene supercomputer with 500 DGX systems, we can train GPT-3 in 11 days, and Megatron Turing can be trained from scratch in 6 weeks. Now, of course, our researchers want to train those frameworks even faster, but it's a great snapshot of where we are today. And with NeMo Megatron, you don't have to train from scratch. With the models we provide and using, you can go through and add your own data and retrain even quicker and develop your own state-of-the-art language models. Now, just as the size of models you need to train increase, so too does the size of models that you need to inference. Triton is NVIDIA's distributed inference engine. It's a great tool to get started on running inference, even if you don't have any GPUs. It was one of our first pieces of software, our first SDKs, that we ported and ran in CPU only. Many of our customers start using Triton on CPU-only nodes and then add GPUs as their model grows or as their number of users and number of inferences that they need to run grow. Triton, of course, started supporting single GPU performance, Again, if you look at inference on the full GPT-3 model, it needs at least 350 gigabytes of GPU memory, more than any single GPU will have for years to come. So multi-GPU inference in train was a feature we needed to add. Finally, to run the full Megatron Turing, we needed over 530, or we needed over 1 terabyte of GPU memory. And while Megatron Turing is a huge model, researchers tell us that they just see that curve going up and up every year. And so with 1 terabyte of memory, we can run inference across 3 DGX A100 servers with 8 GPUs each. So this is amazing. Using Triton, you can take these giant models and not only spread them across multiple GPUs in a server, but across multiple servers, taking advantage of all of NVIDIA's networking technology. NVLink within the server between the GPUs, InfiniBand, and GPU Direct RDMA over Ethernet outside of the server. And one of our amazing products that's catching on across more and more customers. We've talked a lot about our partners so far. And today, very proud to announce with one of our most important OEM partners, Atos, a new NVIDIA plus Atos Excellence Lab in AI. Together in this virtual lab, we're going to focus on advancing 5 different parts of supercomputing technology. One, we'll combine the Atos and NVIDIA research in quantum computing to make it further advances in that field. We'll work on cybersecurity, taking Atos's expertise, providing cybersecurity solutions to commercial customers around the world with new NVIDIA products in the cyberspace. Climate, something's important to all of us. Atos, of course, runs some of the largest climate systems in the world, and we'll cover that in our collaboration. In genomics, we'll also be working with Atos. And finally, on computer vision, that is so important in areas from smart cities to video analytics. I'm very excited about this new Atos lab and working closely with Atos, not only in Europe, but around the world. And of course, we'll be working together with all of NVIDIA's exascale class technologies, bringing them to the Bull-Sequana supercomputer line. Our ARM-based Grace CPU, NVIDIA's next generation GPUs, and Atos's BXI exascale interconnect, working together also with NVIDIA's Quantum 2 InfiniBand technology. So that was just chapter 1. We're going to speed it up a little bit here and talk about cloud-native supercomputing. HPC and AI are going everywhere, not just in the traditional data center where the supercomputer was, but out to large edge instruments and out to the cloud. But of course, this requires your supercomputer to now take on new cloud-native supercomputing types of capabilities. It's an entirely new platform that NVIDIA is introducing. NVIDIA Quantum 2. Quantum 2 isn't just about increasing InfiniBand speeds to 400 gig. It's about so much more. Multi-tenant, bare metal secure isolation, performance, congestion control, Sharp Gen 3, providing 32x the AI processing capability right inside the switch, and precision timing down to the nanosecond level, enabling new levels of performance in applications like distributed databases, as well as enabling the world's cloud and other large data centers to become part of the 5G revolution with software-defined 5G networks. 3 parts to Quantum 2. One is, of course, our Quantum 2 switches. Up to 64 ports of 400 gigabit or 128 ports of 200 gigabit in each quantum 2 switch chip. This allows us to bring a tremendous amount of speed and performance and reduces the number of switches in a large InfiniBand network, reducing complexity, increasing performance, saving costs. We'll have our ConnectX-7 InfiniBand network interface controller, bringing new levels of in-network acceleration. And finally, BlueField-3 InfiniBand, building on top of ConnectX-7 with a new 16-core ARM processor and a number of new acceleration functions. Here's a challenge solved by Quantum 2. A supercomputer customers expect peak performance for specific problems. But when you run that in a multi-tenant cloud, you sometimes have other tenants get in the way, and your execution time spreads out. And this is unsatisfactory for turnaround time on your problem. Now, with a cloud-native supercomputer, performance is isolated to each individual tenant, and it lets you reach that bare metal performance in a cloud environment using all of the quantum software and hardware features. We've already had our first customers wins for Quantum 2. Mississippi State University is using Quantum 2 for their latest cluster. This will be their fourth InfiniBand cluster running at the same time on campus. And one of the great features of Quantum 2, like all the InfiniBand generations before it, is it's backward compatible. So Mississippi State will be able to connect all four clusters without having to upgrade or change the networking in their older systems. Texas A&M, another one of the early adopters of Quantum 2 switches. Now, another feature in cloud native is you need to have zero trust in your data center. We've all heard about cyber break-ins across all sorts of industries and even at supercomputer centers. It's no longer enough to trust a firewall. You need to isolate and accelerate every segment, every host in the network, requiring a zero trust solution. We've been expanding our BlueField ecosystem with a whole range of cybersecurity partners, with just a few of them listed here. Now let's go through and talk about MillionX science. How is NVIDIA accelerating applications a MillionX now and in the future? And what are the sorts of applications that really need this MillionX acceleration? Again, the way we're going to provide MillionX acceleration is not simply by building a faster processor. That's just the start. We'll need to scale out and up across the data center. And we'll need to add machine learning and AI. We really need to take a full stack approach and work with our partners, work with thousands of software developers around the world. Let's jump in and talk about some examples we're working on today. Life sciences is a field that's been revolutionized just in the last few years like no other. Life science, of course, has been a long-time user of high-performance computing. But there's a number of examples here where life sciences customers are going through and combining HPC acceleration with machine learning and AI. One of my favorites is MegaMolBART. The name alone is interesting. MegaMolBART was developed by AstraZeneca and NVIDIA just this year, working on our DGX SuperPod and also running on the Cambridge 1 supercomputer of NVIDIA's. With MegaMolBART, the system was able to generate new molecules that don't exist in any textbook, don't exist in any of the thousands of molecules that have already been identified and tracked. There's 10 to the 60th possibilities of how you can generate a molecule. And this is an amazing advance in this science. AlphaFold now can be used to predict protein structures. This is a key part of drug discovery. And of course, everyone on Earth can benefit from new drugs. In drug discovery, very small molecules of potential drugs need to be tested against hundreds of thousands of protein structures to decide whether they're actually going to cure the disease, the condition. NVIDIA has been working around the world with different researchers in this area. One of my favorite is Entos. Entos is a company that was just founded a few years ago, 2019. And what better to tell it than this short video from Entos themselves, how they've worked with us to provide solutions 1,000 times faster.
Entos, founded in 2019 in San Diego, California, is using NVIDIA GPUs and NVIDIA Clara Discovery to accelerate the development of tomorrow's drugs and therapeutics. Let's take a closer look. Entos has developed OrbNet, a graph neural network that models chemistry at the atomic level, where quantum mechanics governs how atoms interact with each other. OrbNet is allowing Entos to discover covalent inhibitors, for example, against the protein HSP90 shown here. OrbNet is able to predict energies and forces to drive molecular simulations, intertwining quantum mechanics and deep learning. Modeling the electronic structure of molecules allows Entos to simulate how a potential drug will interact with a protein. Here, we can watch as chemical bonds break and form as a candidate covalent inhibitor reacts with the lysine residue of HSP90. On NVIDIA GPUs, simulations with OrbNet are 1,000 times faster than DFT.
It's amazing. Entos has done in just a few years what before them researchers spent their lifetime trying to solve and wasn't possible. Climate simulation, and climate's certainly been in the news with COP26 the last 2 years, is an area that's being revolutionized by deep learning. There's a number of different projects around the world on Earth digital twins, on super resolution for climate models in other areas to go through and improve climate science. And of course, why is climate science, why is accelerating climate science 1,000,000x so important? Let's look at some of the scales where we're at today. Thomas Schultheis from CSCS, the Swiss Supercomputer Center that has done extensive research in climate science, has predicted that this year, or by 2023, that they need to get to 1 kilometer resolution to resolve convection and remove parameterization to improve model accuracy. And they'll be working on their new Grace supercomputer in 2023 to provide just that. But that isn't enough. A second projection says that 100-meter resolution is required to resolve storms and predict extreme weather. We've all seen examples over the last year where unpredicted extreme weather has caused havoc, destroyed property, and destroyed lives. And finally, looking out farther into the future, even more resolution, 1 meter resolution is required to go through and simulate stratocumulus low clouds to reduce uncertainties in climate projections. This requires literally 100 billion more compute than the 2023 1 kilometer model. We believe that the world can't wait to 2060 to reach these sorts of accelerations. That's why this fall we introduced NVIDIA Modulus. Modulus is a framework for developing physics-inspired ML models, a machine learning model that's been trained by real physics. With Modulus, scientists around the world will be able to create real digital twins to better understand large climate systems like never before. It's reshaping the world. Let's go ahead and take a look at some of the things we might be able to accomplish. This is an Earth digital twin in Omniverse. This slide here describes what's going on, taking in different sorts of sensor data, modeling it running Modulus, and then displaying the results in Omniverse. Let's go ahead and roll the demo.
The Fourier neural operator PhysicsML model predicts the precise path of hurricanes a full 4 days in advance and can provide near real-time updates as conditions evolve. Here, we're looking at the massive 2016 Hurricane Matthew. The red line shows the observed track of the hurricane, the contours show the AI prediction, the black dots show how closely the actual path of the hurricane followed that prediction. The white cones show the NOAA forecast. Being able to accurately predict the behavior of complex weather systems around the world is a key step towards building a digital twin of the Earth.
You know, in Silicon Valley, where I live, we've experienced nearby fires across the state. Started off the season with more rainfall than ever, though we're in a year of drought. These sorts of advances can't come soon enough, no matter where in the world you live. Finally, the last chapter. Before I go into this, one last reminder. There's a Q&A window, and if you have any questions, please post them in the Q&A window, and we'll get to them shortly. But first, a few minutes about Omniverse. There's been a lot of talk in the press about Omniverse. And I thought I would take just a few slides to talk about what is it and how does it apply to supercomputing. Many of you today were just infants or in school when the World Wide Web was founded. And you don't remember before. But before the World Wide Web, the internet existed, but it was just point-to-point communications, things like email or FTP for file transfer. It was with the discovery of the web browser and the World Wide Web that you could connect to any company's business site, any consumer site, and get, in effect, 2D data in a standard web browser without having to write a lot of custom code. It just simply worked. HTML is what made the World Wide Web possible. But today, of course, the world isn't just about 2D data. There's so much 3D data available. Various sorts of 3D design tools used in architecture and engineering, used by anyone who has a camera in their cell phone and does some simple photo editing, and all sorts of different tools. And today they don't interoperate. So the first thing Omniverse is, it's a tool for digital content creators. Using Pixar's universal scene descriptor language, Omniverse brings in 3D data from any tool with the appropriate connector and lets users interact with and manipulate the data in their tool of choice, instantly showing the changes in one tool to a different user using a different tool connected by Omniverse with the same connector. The same way the World Wide Web let two people look at two different websites and perhaps type in a document and see the changes in the document at the same time. Only this time, it's 3D data. The second part of Omniverse is, of course, the AI and the science behind it. In the early days of the internet, you had the app server, and the app server provided simple transactional database or other logic that sat behind the data. But of course, in today's world of AI, it's not just simple structured data. We're running robotic simulations, developing self-driving cars, running complex digital twins of factories, all overlaid with that 3D data. in bringing it all together. Omniverse isn't just a concept that we dreamt up last week. Omniverse is something we've been working on our lifetime as a company, and very specifically as a product over the last 4 or 5 years. So let's take a look at one of our partners, Siemens Energy, and how they're using Omniverse today. Let's roll the demo.
This massive heat recovery steam generator uses hot gas exhaust to convert water in the pipes into steam for the turbines. Predicting corrosion to avoid downtime is challenging. Reduced order models aren't extremely accurate, and full simulation takes expertise and time. Siemens Energy is developing a digital twin with NVIDIA Modulus for the multi-phase turbulent flow. With point cloud data to train a physics-based AI model, they can infer high-fidelity flow shown by the streamlines in seconds. This could reduce downtime by 70%, saving the industry $1.7 billion a year.
So that's just one example of multiple customers we are working with today in Omniverse. This will be a huge use of supercomputing going forward in letting the results of supercomputing centers being put to new uses and shared, not just in the data center where they're created, but across the world by anyone. Today, we already have many, many partners connecting virtual worlds. And here's some of the stats and some of the names of some of our partners today. Finally, as Jensen announced last week, we're going to build the world's largest digital twin. I know many of you have heard about our Cambridge 1 supercomputer. Some of our partners like AstraZeneca, GSK, King's College London, and others have been working with us and collaborating on Cambridge 1. Earth 2 will be a similar supercomputer, but for collaboration, not in life sciences, but collaboration around our own planet, building the world's largest digital twin. We're very excited about this, and it'll be designed to use all of our latest technologies, including, of course, Modulus-created AI physics models in Omniverse. So quick wrap-up of what we talked about today. NVIDIA continues to be the #1 accelerated computing platform. It's not just about a fast chip, although we have 3 very fast families of chips. It's about the thousands of applications in data center scale acceleration. The data center is the new unit of compute, and million-x speedups from where we are today are needed. Finally, our Omniverse platform, powering digital twins, will connect supercomputer centers and help them share their outputs like never before. So let's go ahead and bring up our panelists. And I see there's a few questions here. The first one we'll give to Geetika to answer. Geetika, how do you plan to serve big models like GPT-3 into a service that can run at the edge?
Okay, can people hear me now? Okay.
Yes.
Oh, wow, this is a great question. I mean, so the question is, how do we plan to use or serve big models like GPT-3 into service that can run at the edge? So first of all, GPT-3 is a model from OpenAI that is used for generating new language and answering questions. And edge computing, when we talk about edge computing is very anywhere where a computer or any device is interacting with the human world. So I would say that when it comes to edge computing, definitely wherever there is speech required, there is interaction with with a human being who's answering or who's asking for questions or looking for information, that's where GPT-3 can be definitely used for assisting, answering questions to the customer. Now, these can be use cases either in customer service, these could be use cases in retail. So there are various places where this model could be used at the edge.
Great. Thank you, Geetika. Next one for Tim, I think. Tim, here's a question. Can any huge matrix solving compute problem be optimized by CUDA?
Sure. I mean, pretty quick answer, and then I'll give a medium length answer. The short one's yes. You're really only bounded by the total system memory. You can write an optimized CUDA code to solve the problem, even if it's out of core. Of course, I would be remiss if I didn't mention that NVIDIA has a huge set of libraries we built over 15 years, providing highly optimized performance for a huge range of types of solvers. So I would always, of course, recommend checking out what we have there first. Sometimes people are surprised by the kinds of solvers that we already have implemented. For example, we have mixed precision solvers that can take and return FP64 accurate data, but as a black box internally leverage reduced and mixed precision. In some ways, we want to talk about huge problems. HPLAI, that benchmark, is actually really an at-scale demo of that capability, which we have available for users in our libraries.
Tim, I think that's a great answer, and just resounding on some of the themes from earlier, right? Just doing matrix math in a chip is not that hard, right? But really doing it at scale with so many different types of software applications, and doing it effectively all the way from a 3 or 4 watt NVIDIA GPU embedded at the edge, all the way up to currently the world's 6th fastest supercomputer, Selene, #1 leader in ML perf, really requires that full stack approach to acceleration. Here's one for Dion. Dion, is Modulus a simulator?
No. Short answer is no. Basically, Modulus is, I think, as you perfectly described, is a way of providing physics-informed or physics ML neural networks that can then be used to inform a digital twin or just be used for surrogate approximation of simulation practices. So it's really meant to help you accelerate some of your traditional simulation practices using a physics-informed model, and allows you to ingest things like PDEs or GNOs, FNOs, etc. Lots of physics-based algorithms that can then be used to train a neural network and give you outputs that obey the laws of physics.
I heard one of our researchers describe it this way. They said, look, for decades, simulators have been built to simulate the laws of physics. And the laws of physics, of course, are not changing, right? But the laws of physics are sometimes very, very expensive to calculate and to simulate. So he said the way I'm using Modulus is when I have to, I'm actually simulating the laws of physics using all of your different HPC SDKs. But when I don't have to simulate the whole problem, I can actually use data science or AI and go through and solve part of the problem that way and save on computational costs. Gilad, here's one for you. I know I sort of glossed over some of the cloud native quickly. If I'm processing in the cloud and I want to use, or my cloud offers HPC bare metal instances, would I still benefit from telemetry-based congestion control?
Well, the answer is definitely yes. That's the short answer. And regardless if you're running on a cloud and getting bare metal performance, or running on a supercomputer and getting a bare metal performance, you are sharing that infrastructure with other users. For example, let's say that I'm running a CFD code on the system, and my friend Pasha is doing a massive all-to-all operations, and his friend Mark is actually running a massive storage applications, and his friend Gitika is doing a massive data that come from the edge all the way to the main system. Those applications share the same infrastructure, and therefore one application can impact the other application performance. And with the telemetry-based congestion control, we are bringing performance isolation into bare metal cloud or bare metal supercomputer, which means that one application will not harm another application performance. And every time you're running your application, you're going to get the same predictive performance. So the answer is definitely yes. And we're bringing great capabilities with the Quantum 2 platform to enable new levels of performance isolation.
Thanks, Gilad. And I love to talk about our partners, and I forgot to mention that both the Texas and the Mississippi State systems are being delivered by our partner Dell. So thanks to Dell for being a great supporter of InfiniBand over the years and for being first to market for shipping NDR. Nicola, here's one for you. How do you see HPC plus AI use cases evolving for healthcare and life sciences?
Well, very good question, Mark. It's indeed a very exciting time to work in the field of healthcare and life science, and it's evolving rapidly. So we have seen major breakthroughs in medical imaging and genomics and many other fields in the last years that have led to new opportunities. But one of the most exciting developments that we have seen the recent breakthroughs happen simultaneously. So in both biology and chemistry. So you also addressed this in your presentation. And this may really reshape the way of drug discovery will be done. So it will be computational. And every area from target identification to protein engineering are leveraging AI. So some examples you mentioned were OrbNet, AlphaFold, and Rosetta Fold, for example. But believe me, this field of drug discovery is extremely complex, and the models tackling these problems are similarly complex. So some of the successful approaches are, for example, based on transformers, like the SE3 transformer for property prediction, or your favorite MegaMolBart for molecular generation, or the Rosetta Fold for protein structure prediction. Developing this kind of models and simulations requires a system that can handle complex workloads, efficient communication within the system, and secure access. So if you have to keep in mind that healthcare data, life science data is usually very sensitive data. So it's not only a single component, as you said before, but the entire software and hardware stack that really needs to work together to train efficiently and safely. So it does make a difference. And my team, for example, has the pleasure of working with key partners like AstraZeneca, King's College, as you mentioned before, on Cambridge One, so the supercomputer dedicated for healthcare. So really, really exciting field, and I see a lot of development.
Thank you, Nicola. I need to give you a special shout out. This is a hybrid show, and some of us like Gilad and Jack, Tim and I are here at the show in St. Louis. Others are back at our headquarters in California, and I know you're calling in from your kitchen in Germany. And so it's middle of the night there, and it's not quite as fancy as Jensen's kitchen, but thank you very much for being part and dialing in. Jack, here's a question for you. What are some of the different AI techniques that you see the HPC community adopting?
So thanks for the question, Mark. The combination of AI and simulation is really taking off. For years and years, simulation science was working away with steady progress, making comparisons to experiments after the fact. But now, if you will, we're taking our left hand out of our pocket and having it work together with our simulation right hand. And AI and simulation is making tremendous progress. This is happening in diverse fields where the data is available or it can be generated by simulation. To be sure, material science is out in front, as you've mentioned, and biology is out in front, but also in classically very hard areas like computational fluid dynamics, people are tackling the turbulence problem, the last great unsolved problem of classical physics. People are tackling this turbulence problem using AI to learn from data what the physics is requiring of the solutions. So the areas that are going to be explored are just going to be unbounded. And even if we step away from the areas that have been dominated by PDEs in science into those areas like social science and biology and the humanities, all these areas are going to have abundant data, and where data is available, we're going to see AI applied. And as our ability to collect data through sensors is just continuing to progress, this is really a wave that is going to be at the forefront of science and research and engineering for several years to come.
Jack, that's exactly right. I know I was speaking to some of our researchers at University of Florida that, of course, has their Gatortron system there, of one of the largest DGX superpods in higher ed, and they just hired over 100 new AI faculty members, and those faculty members spread across 50 different fields. The most interesting one was forestry. Right? Who would have thought someone from forestry needed a supercomputer before? But now with AI, and think about it, there's an awful lot of unstructured data out there on forestry. Another question for Tim. I can see we've got quite a few questions on quantum here, and that sort of echoes the interest in quantum in the industry. Tim, why is simulating quantum circuits important versus just testing them on quantum processors?
Yeah, that's a great question. And Mark, you talked a little bit about this, but I'll just reemphasize some points that I think have been made. There is just a lot of work ahead of us from here to bring hardware, software, algorithms to the point that useful work can be done on a quantum processor. And that's exactly why NVIDIA is investing in this area, to help the community research the computers of tomorrow on the fastest computers of today. Quantum computers today are small, they're error-prone, so too error-prone to demonstrate an advantage on useful problems. So simulating quantum circuits with classical systems allows researchers to study algorithms at a performance and scale far beyond what's possible on quantum processors today. The result that we saw last week at GTC when Jensen talked about it, and then it was also shown in this special address here, is a great example of this. So we're using cuQuantum's tensor network library on a DGX superpod, and we can simulate a quantum solution to max cut optimization problem on thousands of qubits. That's multiple orders of magnitude above what has been done on a quantum processor. That capability is vital to effectively research quantum algorithms and applications to understand where and how quantum advantage is going to come.
Great, thanks, Tim. Gilad, here's one for you. We had a listener ask, they said, I invested a lot buying a CPU cluster last year with HDR InfiniBand. I want to add a GPU cluster now with Quantum 2. Can I connect my CPU cluster running HDR to my Quantum 2 GPU cluster?
So I'm getting all the yes questions, I guess. So the short answer is yes. Long answer is that by choosing the NVIDIA Quantum InfiniBand platform, you're not just getting the best networking performance, the best in-network computing capabilities and so forth, but you also protect your investment. InfiniBand enables you to connect a previous generation to current generation to future generation. It's completely backward compatible and future compatible. And therefore, you can connect your CPU HDR system to your GPU NDR system. And if you have a storage system that might even be on a different generation, you can connect all of those together. And not just that you can do it, but we have many of our users that are doing the same things. We have actually multiple end users that having multiple generation of InfiniBand in their system, or they're having a different compute structures connected to a different storage structures, and everything works together with the same software, with the same architecture. So the answer is yes, and definitely that's a great benefit of InfiniBand.
Thanks, Gilad. And unfortunately, now we're out of time. But thank you, Gilad, Jack, Geetika, Tim, Nicola, and Dion for joining. And thanks to all of our listeners who joined in to listen to our special address at SC21. We'll see you next year.
Thank you very much, everybody, for attending today's SC21 special address. I want to thank all the speakers for their presentations and the discussions. And we look forward to connecting with you over the next few days at Supercomputing and over the next weeks after that and months to come. And hope everybody has an enjoyable SC21 and talk to you soon. Thanks.